Okay, so for today's video, you guys, I'll try to speak a little bit louder, but we're going to be talking about just using that equation that relates speed of sound with frequency and wavelength. And what we'll do is solve for some wavelengths and take into consideration things like temperature as well. So what we're going to start off with is talk about the temperature of air or water or steel and how that makes a difference in the speed in which we're talking about. So as we mentioned in some of the classes today, temperature, especially in air, has a great deal to do with the speed of sound due to the fact that in hot air, the molecules are a little bit more energetic, and in cold air, they're a little less energetic. And so when molecules are a little bit more energetic, that means that vibrations can occur a little bit more easily between molecules. So as an example, we'll just take a look at a quick visual of this. In hot air, you'll notice that we got a lot of air molecules, but they're pretty spaced out. They're pretty energetic, more energy. When air molecules are a bit more energetic, then they're more open to being vibrated, and they're more willing to vibrate against other air molecules a little bit more quickly. Versus cold air molecules, you'll notice in my example here that the molecules themselves are bunched together a little bit more, and when they're bunched together, due to the fact that they're quote-unquote cold, they are a little less energetic. They don't want to vibrate as quickly against other molecules, and they just have an overall less amount of energy. So as an example of this, you'll notice that in our work today, the temperature then is going to have a direct correlation to the speed of sound due to the fact that a faster speed of sound is due to air molecules somewhat wanting to be a little bit more energetic and vibrating a little bit more quickly against other ones in hot air than in cold air. So let's take a look at an equation we can use that takes into account temperature. So if I want to know what the speed of sound is based on the temperature, then since we're using the metric system, we're going to be using Celsius. The velocity of air can be found by starting with the velocity of air at 0 degrees Celsius. And this has been found through several trials and is just kind of like a well-known standard that we use for speed of sound through air. 0 degrees Celsius correlates to a freezing temperature. Alright, so that takes into account our standard. So what we'll do is either go up or below that standard based on the temperature. And the way we do this is by adding 0.606 times whatever the temperature is at that point. So if it's 20 degrees, then we'll multiply 0.606 by 20 degrees Celsius. So what does that 0.606 actually mean? Well, that's actually 0.606 meters per second that's being gained with every temperature difference in 1 degree that occurs in our air. So in other words, that 0.606 is an increase in speed for every 1 degree Celsius temperature gain or change that's occurred. So if the temperature just changes 1 degree, so let's say 0 degrees to 1 degree, then we gain 0.606 meters per second. So we're basically gaining about 60%, we're actually gaining 0.6 of a meter per second of velocity with every temperature, 1 degree temperature increase. Okay, so let's actually take a look at a problem such as this, and these problems are going to be pretty basic, but we'll go through them anyway just to show how we're using this equation. So when the C4 key on a piano keyboard is pressed, a string inside the piano is struck by a hammer and begins vibrating back and forth at approximately 262 cycles per second. What is the frequency and wavelength of this note? Well, the frequency is actually given to us. It's 262 cycles per second. So what that means is 262 cycles per second is equivalent to 262 vibrations per second, and that is equivalent to 262 hertz, which again is just our representation of frequency. And you'll notice that this corresponds to the C4 key on a piano keyboard, which is that key. And you'll notice that C4 is about 261.63 hertz, or vibrations per second. So now that we have the frequency, which we already had somewhat in that problem, then what we're going to do is use that frequency to solve for the wavelength of this note. So how much distance does one of these waves cover in an amount of time that it's given? So we're going to use our equation, and this is our frequency, 262 hertz. We're going to use the equation V equals frequency times wavelength. Now notice it doesn't give us a temperature, so we're going to be using 343 meters per second. And where did I get this for 343 meters per second? Well, that's the speed of sound at 20 degrees Celsius. And 20 degrees Celsius is about 68 degrees or so Fahrenheit. So this is kind of a standard speed of sound that is used in a lot of physics classroom, just based on the fact that 68 degrees Fahrenheit is kind of room temperature. It's a pretty normal temperature to use, basically. So if it's not listed in the problem as far as a temperature, then we'll just use 343 meters per second and assume it's at about 20 degrees Celsius or 68 degrees Fahrenheit. Okay, so let's go ahead and solve now for the wavelength of this specific note. And by doing so, we'll be using this speed of sound and the frequency that we have in our equation. Velocity, or speed of sound, equals frequency multiplied with wavelength. So the velocity we'll use is 343 meters per second, and our frequency is 262 hertz, and we will be multiplying that with wavelength. Alright, so to isolate wavelength, we're going to go ahead and divide both sides by 262 hertz. Now you'll wonder, well, how are we going to get a wavelength in meters when we're trying to cross out meters per second in hertz? Well, hertz just means 1 over seconds. So per second, that's what a hertz means. So you'll notice that per second will cancel out with the per second on top, and we're just left with meters. And so 343 divided by 262 gives us a wavelength of approximately 1.3 meters. So one wave covers 1.3 meters of distance, but we have 262 of those waves occurring every second. So we're covering 343 meters every second that goes by. So the wave itself corresponds to the frequency. So a shorter wave like that corresponds to a little bit of a higher frequency or a higher pitch. And actually on the keyboard you can see that C4, or 262 hertz, is actually not very high and it's not very low. It's kind of a medium frequency. Okay, so let's go ahead and take a look at another problem in which we do have a temperature change and see what that does to the wavelength. So, a male vocalist with a bass voice can sing as low as 85 hertz. What is the wavelength of this pitch? What is the note being sung? I guess we're assuming in that problem it's 20 degrees Celsius. Now, if he sings this pitch in 0 degrees Celsius freezing conditions, what is the change in wavelength than what was given above? So 85 hertz, the notes being sung there is somewhere between E2 and F2 on the keyboard, so we can see that's a pretty low pitch, a low frequency, a low note on our keyboard. That would be somewhere between those two keys. Alright, and let's use our equation, V equals frequency times wavelength, to solve for the wavelength at 20 degree weather, or 20 degree temperature, excuse me. So 343 meters per second, which is the speed of sound at 20 degrees Celsius, is equal to 85 hertz multiplied with wavelength. Divide both sides by 85 hertz, Again, we can do this because hertz just means 1 over seconds. So the per second on top cancels out the per second on the bottom, and we're left with meters, and the wavelength becomes 4.03 meters or so. So you can see the change. With a lower pitch, we have longer wavelengths. So less pitch leads to more wavelength. Okay, so what about 0 degrees Celsius weather? Temperature, excuse me. So at 0 degrees Celsius, we already established that that is 331.3 meters per second of velocity, and that'll be equal to 85 hertz, and that leads to probably a change in the wavelength, and cancel out, and the wavelength is going to be equal to 3.89 meters, which is about 3.9 meters. So with a 20-degree drop in temperature, which is going from basically room temperature, 68 degrees, to freezing, the wavelength changes by 3.9 or by 0.1 meters. So not a huge change with wavelength. Now, what we're going to see later on is that doesn't seem to be a big change in wavelength. However, if we're looking at two different frequencies with very, very slight changes in wavelength, then that does cause a change in note perception, I guess if we call it that. Okay, so that's kind of just looking over a couple of problems. I also have a reading attached to this note on a reflection, and what I'd like you to do is go through the reading as well, and that'll be part of your notes. So this will mark the end of the video, and then I'd like you to take a look at the reading, and the goal is to come in tomorrow with knowledge on both how we're using this equation, which I think is pretty simple. It's a one-step equation, and what did we glean from the reading as well, and how does it apply to what we're talking about.